So let's look at it. So here we go. So we have quiz 1. Let's take that color. So we have quiz 1. Question 1. At the instant a traffic light turns green, a car that has been waiting at the intersection, V1 car, V1 initial is 0. Is that how you've been parsing it? Okay. Starts ahead with a constant acceleration of, so that's A1, 3.60 meters per second squared. At the same instant, a truck traveling with a constant speed of 25 meters per second overtakes and passes a car. So V2 equals truck. V2 initial is 25. What's the acceleration? A2 is 0. And now we know that X initial, let's choose that to be 0 meters. And it's the same for each one. How far beyond its starting point does the car overtake the truck? Well, I don't know. I guess that's what the problem is asking us. Well, let's look at it graphically, because we've worked a lot on this, right? So what would the graph of position versus time for the truck look like? Steady slope, straight line, okay? Where does it start? 0. That's what we chose, yeah? So this is part 2. How about the car? What's its position versus time going to look like? A parabola. What would be some points I would be careful to show on my graph? What's its original position? 0. What else is 0? On the position graph, what else will be 0? The slope, because it's at rest, yeah? So I'd expect to see something like that, maybe with a little bit of motion off the graph, but you know, I'm just not known for my artistic skills. There you go. So when the truck is overtaken by the car, what condition has to be met? How do we know it when that happens? Anybody? Yeah, that's right. So let me call that X final, and that'll be at T final. Yum yum? Okay. So what is X for uniformly accelerated motion, constant acceleration? X equals X initial. Is this the car or the truck? It's both of them, right? Please always start with the equation as it is shown on the formula sheet. Always start with what's written down before your eyes so that you're less likely to make a boo-boo. Now, let's apply it to this situation. So we're going to have X1 final equals X2 final. That's our condition. That's our payoff. Now, for X1, what is the initial? 0. What is V initial? I'm starting to like this algebra. What about 1/2 AT squared? Yeah, 1/2 A1 T squared. What's it going to look like for X2? 0. V2 initial, which is V2 therefore after, plus 0. Everybody see how I've used the named quantities up above? I haven't used any values. because values would just clutter up my workspace. So if I bring over, I'm always scared of the quadratic term, I bring over the V2 initial t, I'm going to have that result. No thanks. I appreciate that, but no thanks. Get out of here. Okay. So, what can you tell me? Let's factor out a t. So either t equals 0 or 1/2 a1t minus v1 initial equals v2 initial, excuse me. So we get that t final is equal to 2v2 initial over a1. This is my solution. This gives what I want in terms of the labels that we have used to describe each quantity precisely. By writing it in this form, hopefully I will see this answer repeatedly during other problems. That's why we don't write numbers. We want to see the commonality of working these problems. Let's look at units. I have just to check it, meters per second over a meter per second squared. So that's a meter per second times second squared over meter. So at least with the units, I'm pretty well. Let's look at the limits. Suppose that truck is booking down the road. V2 gets bigger and bigger and bigger. What is that going to do to the time to overtake? Yeah, it's going to take the car a bit longer to get to it. Suppose instead, V2 initial is whatever value it is, but now we're talking about, I don't know, a Porsche. Okay? Let's let A1 be really big. What does that do to our time of catch-up? Yeah, so it's down in the denominator. Okay, so I get that TF is going to be equal to 13.9 seconds. Did he ask us for that? Okay, so what can I use to get X final? Yeah, so I can use like 1/2 A1t squared, right? Whatever. Or good. A1t squared. And I get 347 meters. Yum, yum? Yes, sir. You can do whatever you want to do it as long as it's consistent with the laws of physics. I'll be happy to follow what you do. Okay? We sort of already used calculus to do this problem by deriving from A equals a constant the equations of motion. Pardon? Well, let me look at what you did. Okay? Ibrahim, let me look at it. I'll see if I can follow what you did. Okay, I'll look at it. It's okay. Okay. There we go. Yeah. Wednesday. Yep. Okay. How about the second problem? Now we get to use calculus. Everybody say yum yum. So t equals 0, x initial equals 0. At t equals 0, a particle leaves the origin with a velocity of 9.0 meters per second in the positive x direction. So, v sub x initial is positive 9. And moves with an acceleration of a equals 2t. At the moment, the particle is at x equals 15 meters. So we're going to have, let's call it x2 equals 15 meters. What is the magnitude of v2? They want the speed, so if it wants that to be negative, we'll take the positive. Yum yum? Okay. So, how do we start? We need a position relationship and a velocity relationship. May I use what I did in the previous question? Why not? Exactly, it's not uniformly accelerated motion. Well, if I can't use all those beautiful equations, where do I turn? I turn to the definition. A is dv dt. Yeah? So we're going to get the integral of a dt, which is the integral of 2t dt times a out front. No, a is 2t, excuse me. And we're going to get t squared. Right. Plus c. And that's going to be equal to the integral of dv, which is v final minus v initial. Well, at t, I mean, we didn't say what c was, but at t equals 0, what does a look like? 0. So I'm going to get hopefully something like t squared minus v initial equals v final. What is v initial, though? Positive 9. So I'm going to have t squared minus positive 9. So that's going to be, whoops, sorry, you're right, thanks, should be on the other side. So I'm going to get t squared plus 9. Questions? Comments? Well, when I rearrange these terms, I'm going to get a dt equals dv. So in order to get that, I have to integrate both sides independently. Okay. Are we ready to get our answer? No. Why? What's the condition? What was specified? We need x2, don't we? Right? So what do we have to do? We have to go back to the definition. Y'all just hair trigger on the integration, aren't you? V is dx dt. The equal arrow means thus, it follows. V dt equals the integral of dx, which is x final minus x initial. Well, that's the integral of what? T squared plus 9 dt. Yes? No, that was given. Right? Well, I mean, no, we don't have to get that one because we said a at 0 is 0. Otherwise, I'd have to have specified it. Excellent question to ask during the quiz, but without loss of generality, we could just set it to 0. So, X final minus X initial is going to be what? T cubed over 3 plus 9t squared between 0 and t. Oh man, I don't get to say squared again. I don't. So between the limits of 0 to t, so we do get t cubed over 3 plus 9t. So what was x initial? 0. And our condition is x2 equals 15 meters. Yeah. So I want 15 minus 0 equal to t cubed over 3 plus 9t. And here's where I got into a bit of a boo-boo, because that's a cubic, bit of a toughie to solve. Apologize, I didn't mean for that to happen. So y'all probably have the fancy calculators that can do that. The way I do it is to put in put in 1 and see what it gives me, put in 2, see what it gives me, and sort of work it down. So when I got that, I had t about equal to 1.6 seconds, and that works out to be v is positive 11.4. Since I hadn't shown you numerical approximation, whatever time you got, I mean, once you get to this step, we're good. And you set it equal to 15. Is that right? No, yeah. Okay. That's tricking you. Yeah, I've always felt uncomfortable moving the DTs around like they were chess pieces, but they tell me it works in math. You have a question, sir? I did. Oh, if you wanted to work backwards and re-derive it, as Ibrahim said, yeah, man, go for it. You're sort of going around your elbow to get to your hand, but as long as it's logical and you show me what you did, I'm thrilled. If you show me magic runes and horoscopes, not so thrilled. Questions? Do you understand what I'm looking for as far as what I grade, what I look for, where points will be allotted? Do you think you'll get any points for this? Yes. Do you think you'll be given points for this? Yeah, it's part of the process, right? Okay, good. So again, any questions for me? Sure. Is that enough? Okay. Magnitude and direction components, I strongly suggest that you do that by drawing the vector by itself and focusing on getting the components. Um, Doing the addition of vectors or subtraction of vectors or multiplication by scalars. If we multiply a vector by a scalar like 5 or pi, how do we achieve that result? Yeah, multiply each of the components by the same factor. Distributive property over each component. How do I go from components, Cartesian components, back to my polar formation, get the magnitude and direction. That's how it should go for you. Quick. Magnitude, since we have both components. What? Yeah, that's right. That's why pictures are so nice, especially if they're in pink. Cartesian means that the two components are at right angles to each other. So r is the square root of r sub x squared plus r sub y squared. And tangent theta is ry over rx, as appropriately interpreted in quadrants 3 and 4. So that should be like brushing your teeth. I don't need to be there saying, go up, go down, go up, spit, go down, right? It is a skill, a very important skill. Yes, sir. Well, when did my clock start? That's my lower limit. What's my upper limit? Well, if I want to create a formula, a relationship, I just put in a generic t. I bet a not insignificant number of you, when you got to t squared, said, hot diggity dog, let's go get position. We're changing position. And we forgot the lower limit, right? Because that was I'm sorry, hold on a second. Let me just go here a bit. Yeah, the V initial was equal to 9. Yep. That's part of that's part of that graphing thing where I think they're mutually supportive. So we've spent quite a bit of time on graphs and interpretations in this class. So you might see on your test a question about that, since we focused so darn much time on it. Okay? Yum yum? Great. So please check your WebAssign due dates. I have moved up the WebAssign for Chapter 3. Why? Because we have a test coming up, right? Monday? Barring Monday? I'll give it to you on Friday. Okay. If other than what flow tells us we need to do, right? Flow. So I wanted to have the opportunity to talk with you, discuss with you, and answer any questions you had before the test. I hope to make that happen more regularly. But I think I've opened up Chapter 4 as well, if not 5 and 6 already. I'm not sure, but please check that. Okay, so what is Chapter 5 all about? Is Chapter 5 or Chapter 4? This is Chapter 5. We did Chapter 4, right? That's the next one. You know, if I knew how to count, I'd be really popular with people. You want it to be on the test? I'll take that under advisement then. Yeah, Chapter 4 is our most recent. Whoops, come on up. There we go. Our most recent endeavor. So I think I mentioned, we've discussed, Cartesian components pay off, right? We can take two-dimensional or three-dimensional motion and we can reshape it into components that are perpendicular and therefore they have nothing to do with each other. And so we have a set of one-dimensional motion. The labeling of x, 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 vx, ax versus y0, v0y, or v initial y, ay, is critical. Because under test situations, some students get really, really, really excited about putting in g for every acceleration they see. So, cautionary comment. As we've discussed before, displacement is a change in position. It doesn't tell you how you got there. It's only concerned about the end and beginning. So this would be in the x direction, it would be in the y direction, and it would be in the z direction. So now I am going to be even more eager to call out things that are vector quantities. And how will I do that? We've talked about this. How do I show a vector? Yeah, put an arrow over it. You cannot put an arrow above a letter and not think vector, unless it's February 14th, in which case Cupid's got bad aim. Okay? It is important, I think, for your success to use that religiously, constantly, consistently, because that will be a tip to you to think about components when needed. If you sort of skate along, who cares, what the heck, well, it's not going to end up well. It'll be the same train wreck as if you were to solve the problems without using subscripts. Okay, enough admonishment. So, everything we had before, we now explicitly say is a vector. So V becomes delta R over delta T, or V average becomes delta R over delta T. You can also write that as, when I get my ink, you can also write that as V vector with a bar over the top. Not a tilde, but a bar over the top. That's mathematically communicating the mean value of the vector V. Okay. Again, is speed equal to the magnitude of the average velocity? No, because it depends upon the distance traveled, not just where you end up. Is instantaneous speed equal to the magnitude of the instantaneous velocity? Absolutely. Since it's just an instant, you don't have a chance to take a side trip. Okay. Acceleration. Notice how we can find the acceleration from the velocity graph. We can look at V1 versus V final. You can use the parallelogram method if you want to. Yeah? And remember, that's the parallelogram that would be completed like that, I guess. So the sum would be over here, but notice what the difference is. The change in V is the vector you need to add to your initial velocity. Therefore, its tip or its tail is put at the tip of V initial, and it winds up at the tip of V final. So that's delta V. Again, instantaneous. Each of these can be considered over finite limits or in terms of their derivatives, mathematical functions. So, in general, that's what we'll sort of do. You know that I prefer to have r sub x and r sub y instead of just x and y. Um, I do like to have the I and j component set. So I love how they wrote the velocity function. And if we have constant acceleration in multi-dimensions, that means not only its magnitude is constant, but also its direction, and I can find the components of the acceleration. And each of those will be constant. And so again, I can use the relationships we obtained for uniformly accelerated motion and obtain the results for either the I component or the j component. Okay. Bum, 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 bum. So this is sort of a repeat of what we just did in chapter 3. Okay. Now, free fall is a special case. Free fall says it falls freely. That is, it is only under the influence of gravity. All of the forces, like air drag, are negligible. Free fall does not apply to a parachutist who is falling at terminal constant velocity. So free fall is what you would experience if you were jumping above the Earth or the Moon, more appropriately, and there were no atmosphere. The path that is taken by the particle is called trajectory. Everybody say that. Trajectory. Awesome. So let's get out the magic tennis ball again. Um, Excellent. It's not a complex discussion of Plato's, shadows in a cave, okay? So if we were to draw on this image, the acceleration, we know that the acceleration is down and down and down and down. But what is the acceleration at the top of the path? The acceleration is what it is at any other place. It's always g. What is 0 at the top of the path? Not the velocity. Again, velocity has components. It's very tempting to say that it's 0, but that would be motion where the ball goes into the air and stops and then falls. It always has the horizontal component of velocity. The velocity is a minimum magnitude at the top. Sorry, yes? We'll talk about acceleration. Oh, yeah. Acceleration is really the curvature of a YT graph. So if we assume that this is a nice uniform parabola, then acceleration is constant from our graphical interpretation. Well, let's look. V is what? The square root of Vx squared plus Vy squared. Now, can we do anything to Vx without involving a baseball bat? When it's in free fall? It's constant. So we can't change that first term. But what about the second term? What about Vy? Can Vy ever be 0? At the peak of motion. So that's when I said that V was a minimum at the top. There is no Vy term. It's 0. So that makes it a minimum. Okay? Again, Vy is 0 at the top, but acceleration is not 0. And again, if you ask yourself about acceleration, you can just ask yourself, as we will see in chapter 5, about the force. Is there any force other than gravity that appears when it reaches the top? Do magic fairies suddenly appear with their stardust? No. Now, I like this. Why do I like this? Yeah, if up is positive, then it will be a negative times the number 9.8 in the y direction. Negative tells us down. Now we can write this as an extremely ugly form, but we'll tend to focus in our problem solving on one component at a time. The only thing that remotely comes to be ugly, though we'll try to simplify it, is circular motion. So often R is used as the range of the particle, which is the displacement in the horizontal direction between the initial and final positions. That's the range. Maximum height is where what is 0? Vy is 0. So we're going to solve Vy equals 0 equals Vy initial plus a sub yt. That's what we're going to use. And that condition will give us the time at which it reaches maximum height. Is there a 1/2 somewhere? There is a 1/2. Where? You were looking for that 1/2 AYT squared. Is Vy initial at the top 0? No. Why? What is Vy initial? It's the velocity in the vertical direction at the beginning. Vy is 0 at the top, but it being 0 doesn't change what it had at the beginning, at the outset. If I find you using this equation, and I don't think this is on the formula sheet, if it is, I'll take my 6-shooter and blow it away. I do not want you to use this relationship on a test. I'm not saying it's invalid as long as you're firing from one height and coming back to that height, but it's a plug and chug. I'd rather you understand how was that obtained by the components. Notice this is definitely not valid if the initial and final heights are not the same. That's another reason I don't like using this formula. It's a nice way to check your work, but it's a crutch you don't need. So again, if I'm allocating, expecting you to do the components and solve for R, and you give me this, how much credit could I give you for regurgitating this? I'm going to give you 0 for that. So you lose all the points I've allocated for obtaining it by using first principles. There is kind of a neat thing, which is called the range of the projectile in terms of the angle. Since the range goes as sine of 2 theta, then theta is going to be 45 degrees for maximum range. And so as you see, for every angle below 45 degrees, say this one is 15, the angle above that will be what? 45 plus 15 is 60, right? They will have the same landing spot. This would be useful, for example, in a snowball fight. You take a couple of snowballs, you lob them at your target, and just as they start to descend, you fire some more snowballs on a lower trajectory. Now, it's going to take less time for the lower angle to reach the target, isn't it? Wilmington, North Carolina. Well, Wilmington is a port, and so here is North Carolina, here's Wilmington, and there's a river, Cape Fear River. Off the coast of Wilmington are the barrier islands, right? So in order to approach Wilmington to capture it, you first have to capture the barrier island. The neat thing was the fortifications at the end, the fortifications at the end various broken things, and they take control of Wilmington. But when the troops marched down the island, they found the rebels full of vim and vigor, and very few of them were dead. Kind of surprised the soldiers. It's almost every time you predict something in warfare, it doesn't happen. Okay? As Eisenhower said, yeah. What was it again? Right. No plan survives first contact with the enemy. Things are going to happen you can't anticipate. But in order to have success, you must have had a lot of planning for that contact. Okay? That was important. So, why was it the Confederates weren't blown out of the ground by these attacks? Pardon? Not really. It was, as we're going to learn in a few chapters, momentum transfer. That is, on the outer banks, there's a lot of sand. Think about it. Sand versus, say, Fort Sumter, concrete and brick. When a cannonball hits sand, it's an extremely inelastic collision, as anybody who's ever hit a golf ball into a sand trap is well aware. Okay? So what happened is the balls just stopped. And so not many people were hurt by that in the initial bombardment. So it was taken, of course. But again, collisions, elastic, inelastic, we're going to get there. Um, if you take air drag into consideration, who held the long jump record in the 1900s, set at 1968 Olympics in Mexico City? Yeah, Bob Beamon doesn't have the record now. Okay, did Carl Lewis break it? Someone else? Anyway, it's broken. Ideally, you would expect to leave at 45 degrees to get the greatest distance possible. But if you take air drag into account, not that I would ever be able to do the difference, it turns out that, whoops, didn't show that too well, did I? 43 degrees is optimal. And at that world-class training, apparently, you're able to do that. There was another thing. Anybody know about Mexico City's geography? What about, okay, don't make me beg. It's a landfill in a lake, okay. Very mountainous. It's very high. So the acceleration of gravity is smaller. Not enough to justify this, but it is smaller. Yes. So I think the decrease in gravity is more than outweighed by the decrease in oxygen content of the air at higher altitudes. But anywho, Bob Beamon had the world record. So hints on solving, I'll let you read those. Non-symmetric, again, your final and initial heights are not the same. Notice, for this case, in order to find out where the projectile hits, what condition must be met? What says you've arrived? Velocity is zero, so it's going to be going falling. When what is zero? Vy? It's falling and it's going to say and stop just before it hits the ground? There you go. What position? Vertical. Oops. Not zero. It's y equals zero if I choose this to be my coordinate system. You could choose this to be your coordinate system, and then y final would be negative the height of the cliff. Don't be misled by the related problem, often called the firefighter problem. You have a building, yeah, flames coming out of a window, and so the firefighter does what? Throws up some water. Hopefully, not always, able to reach that height. That's why they have engines that are called, they have a special name, they're called pumpers, because they can pump the water, not just use the ambient pressure coming out of the fire hose, but they can pump the water up to high pressure. So you don't want to be on the 10th floor with an 8th floor pumper. Okay? What's the condition in this case? They are different but the same. Okay. I could take my fire truck and I could send my water like that, so it's moving down. Yeah. When you hit the wall, once you see it, it's like, oh man, it's x final equals d, the distance to the wall. So it's what we would call a horizontal constraint rather than a vertical constraint. Hmm? Right. Whatever's saying you're finished. Do you hit the wall? Do you hit the floor? Do you hit the ceiling? Yeah. And notice it's possible with the D condition to have two angles that hit the same horizontal position, one above, one below. Okay? So you have to read the question carefully if you're asked what happens. They may ask, what's the soonest time for water to reach the wall? And you would say, that's on the way up. Sometimes they won't tell you. You'll solve for x equals t or whatever, get two roots, and you have to sort of figure out which one's meaningful. For example, it would be certainly within the realm of possibility that you could fire this, I guess, sort of like this case, where it hits it on the way up, but the math says it can hit it later even though it's stopped at the wall. So you have to play those things. You know it's on the way up, on the way down, because what? What? Gravity's got a role to play. So if you were to be asked, is the water when it hits the wall going up or down, what would you do? What would be your constraint? What would be your condition? Diagram really helps. Okay, has it reached the maximum? Or you had another way of saying it perhaps? Is the y component of the velocity positive or negative? And I have had people solve that. Y equals zero at a certain time. Does that happen before or after it hits the wall? That's legitimate physics. Yeah. Hmm. I don't know. I just give you the problems. I don't know. But I think it would be fun to try. So let's do something like that, okay? Okay. You know what? That was on the other sheet. I know. I added it to the wrong sheet. So here's the case. Um, you are knocking down snow. You ever see the movie Mulan? Okay. So sometimes you'll fire a charge into the upper regions of an overhang of snow in order to cause an avalanche, to remove that threat from that area of the trail. So here's the problem. Mulan, of course, she doesn't have long hair. She's playing a boy. And here's Mushu, right, the dragon. And they're going to fire their whiz bang cannon to try to hit that uppermost part of snow. That is, they want to hit here. And let's say that it's a distance of, I don't know, 120 meters away horizontally. Okay? Let's assume that the impact height is 200 meters and that the projectile is on the way down. What are the conditions for the initial speed, initial magnitude of velocity, and the angle so the projectile will follow that path? Do not try to solve this, okay? The mathematics can sometimes be a little bit hairy here, but set up the equations, the relationships, until you're about ready to do algebra. What's the initial speed from the cannon, and what angle above the horizontal does she have to have in order to hit that spot in the snowbank on the way down, so the projectile hits it there? Tell you what, let's take 15 minutes to figure that out. Okay? Work in small groups. Go outside, take a short break, relax, and we'll solve this at 11:30. We'll solve this at 11:30. Okay? Thanks. So y'all can walk around, relax. Yes. When have I ever told you you could not ask questions? I'm not guaranteeing the answer, though. This is a sketch, right? A sketch is pretty. Mulan's got beautiful hair. Mushu is spouting fire because he's got to light the darn thing, remember? Mushu. But we need a diagram, don't we? We need something with a bit more detail. So, look at this. So we need a description. So before I can do any algebra or any physics, I've got to choose a coordinate system. It can be the base of the cliff, it can be wherever you want, but I've got to choose that in order to write out the relationships. And I've got to name things. I got to baptize them. I'm going to call that H. That's a bad idea. Why? H is usually vertical, so I'm going to call that big D. And I'm going to call that big H. Okay? And here's my initial velocity. Can I draw a big arrow? I can. May I draw a big arrow? You have that power. Use it wisely. So this is V initial, and this is theta initial. I chose that origin. You can choose one yourself. That's why I keep stressing to y'all. There is nothing sacred about this origin. But you have to make a choice. You have to commit. Until you choose an origin, you're just going to sit there sucking your thumb. How can I tell you a story if I don't know where it begins? Okay. And we said down. That was our other constraint, right? So, D is 120 meters. H is 200 meters. Vy is less than 0. Vy final is less than 0. That gives us the down. Theta is 65 degrees. Let's write out what I'm trying to find. V initial and what? Time. Yeah? Yes. Oh, yes, sir. Okay, good. So now, what else do I need on my diagram? I have to have one more thing I have not yet described. I need to show accelerations, right? See? You got to commit. You got to show its direction. So, this problem seems to be replete with position stuff. What relationship do we have for positions with uniformly accelerated motion? Yeah? So X final is big D. X initial is 0. V initial X, I'm just going to leave it like that. And what is AX? 0. So what I like to do is I can't do much with that by itself. I'm just going to underline it. Why do I underline it? Yes, I can find it later, and I don't have to look through all that algebra mess to find it. Also, most of you tend to solve your problems in an array that looks like a cotton ball. Tell a story down the page. We've had the little paper time discussion. Okay. Well, it moves left and right. What else does it do? So what do I do first? Excuse me. I write down the universal relationship that I have. I apply it to this situation. What's my final vertical position? H. What's my initial vertical position? What's my velocity? I'm going to put VIYT plus 1/2. What's A sub y? Negative G. It's G down. So the down is the negative sign out front. Yum yum? So these are the two relationships I need to solve algebraically to get V initial. Now, I'm going to need a little bit of help here, because instead of having V initial X and V initial Y, those are two unknowns, it's really only one, right? So I draw a large, maybe not Paul-sized, sketch to the side to remind me, what am I looking for? And I say this is the shy side, and this is the cozy side. So I can substitute for Vx initial and Vy initial. D equals V initial cosine theta initial t. What are my unknowns in this relationship? I've got that, and I've got that. Yeah? Let me apply that same logic to the other relationship. H equals V initial sine theta initial t minus 1/2 gt squared. Where are my unknowns hiding? Here, 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 and here. That's what I asked you to obtain. That's the end of the road with the physics. The rest is algebra. Set up, but do not solve. Yes, sir. Two equations and two unknowns. Can you do that? I know you can. I hate quadratics. So I would write t is d over v initial cosine theta initial. And then I'd shove it here and I'd shove it here. So I'd have some ugly sines and cosines and g's, but I'd have a quadratic in terms of v initial. I'd have a v initial squared here. Oh my goodness gracious sakes alive. I would have a v initial squared here as well. Isn't that amazing? I don't even have a quadratic. Now, when I solve for time, I'm going to get two solutions, right? There's a quadratic. Here's Mushu and Mulan, right? Well, this is the height of the snowbank. We want it to go past the first root, the smallest root of time, and have it hit at the second root of time. That's the whipped cream and cherry on top, okay?